Hello everyone, welcome to IIT Gate classes. This is lecture 11 on TOC, and in this lecture we are going to start chapter 3, that is CFLs and PDA. Okay, so first let me discuss the syllabus of this chapter and then we will jump to the first topic, that is ambiguity in CFG. Okay, so total we have to study 5 topics, okay, in this chapter. First is ambiguity in CFG, second is reduction of CFG, third is normal form, then PDA, and then DCFS. Okay, so let me start the first topic, that is ambiguity in CFG. Okay, so before starting this topic, let me build some background. Okay, and then I will jump to this topic. Okay, so the very first basic term which we should know is parse tree or derivation tree. Okay, so let me take some example, or let me give you some example, then I will read all these points for you. Okay, so let me give you a very basic example. See, let us suppose we have a grammar, or you can say context free grammar, like this: S implies ASB or null. Okay, so now when we are deriving strings, let us take a string, say triple A triple B. When we are deriving this string, then we can make a tree like structure like this: S implies ASB, then S implies ASB, then S implies ASB, and then S goes to null. Okay, so this rooted tree like structure which I have made, this is known as parse tree. Okay, so what exactly is parse tree, or it is also known as derivation tree. So what is parse tree, derivation tree? See, the process of deriving string from a context free grammar resembles a tree like structure. This is known as parse tree or derivation tree. So let me read the first point for you. See, process of deriving strings from context free grammar resembles a rooted tree like structure called parse tree. Okay, next point is, see, uh, is this parse, how you can think. See, the parse tree is, you can say, a inverted tree. Okay, because in a normal tree, okay, I think everybody has seen a tree now. In tree, what we have, these are some roots, okay, and then here we have some branches and so on. So this is a general tree. So in a tree, root is down and branches are up, but in this tree, this is known as root. Let me use a different color. Okay, so root is what? Root is a node which do not have any parent. Okay, so for this, you can say this node, this is the parent. For this node, this is the parent. For this node, this is the parent. For this node, this is the parent, and so on. I think these are basic things which you have already studied in data structures and algorithm. I am just repeating these points. So here root is above and branches are below, hence we call this tree as a inverted tree. Okay, so see the second point: parse tree is inverted tree because root is present on the top. Okay, next point. Next point, see what is the yield. Yield means fruit. Yield, or you can say fruit. Yield or fruit is what? Yield or fruit is concatenation of leaf nodes from left to right. Okay, concatenation of leaf nodes from left to right. So what is the yield? Triple A triple B. I am ignoring null because of obvious reasons. So it will be triple A triple B. Hai, you already know null B is nothing but B only. B dot null is nothing but B only, and so on. So like that only I have said that the string will be triple A triple B. So this is known as yield of tree. Yield is nothing but a string. Okay, so I hope I have made the point clear. And in yield, you have to remember that we have to take terminal symbols only. Okay, so in parse tree, leaves, or you can say nodes which do not have any children, you already know about all these things. Na? Leaf. Okay, so leaf is what? I'm not writing. See, just to save the time, leaf is what? These are the leaf nodes. Na? This, all these are leaf nodes. So leaf nodes are the nodes which do not have any children. Okay, so leaf nodes should be terminal symbols only. They cannot be non-terminal. So what I want to say is, if I write like this: S implies ASB, S implies ASB. Okay, so what can you say about it? Is it a parse tree? No, this is not a parse tree. Why? Because when we see the yield, or you can say leaf nodes concatenated from left to right, we are not getting a string, because here we have a non-terminal, that is S. So this is a sentential form. This is not a string. This is a sentential form. So in parse tree, leaf node must be terminal symbols only. Terminal symbols or null. Okay, I have already told you null is not a terminal symbol, so please remember this fact. So we should say that the leaf nodes of parse tree should be terminal symbols, or you can say null, and nothing more than that. Okay, so non-terminals are not allowed. Okay, so yield is here sentential form now, so this is not a parse tree. Please try to remember this fact. So let me read the third point for you. Yield of parse tree is concatenation of leaf node from left to right, and these leaf nodes must be terminal symbols. Let me underline this for you. These must be terminal symbols. Okay, otherwise OTW means otherwise it is not a parse tree. Okay, so please try to remember this thing. So in parse tree, leaf node should be terminal symbols only. Okay, now let's jump to the next slide. See, I have written S implies AS, B or A while deriving triple A power 3, B power 2 means what? Triple A, double B. What is the height of the parse tree? Height is very simple concept. Okay, so let me draw a parse tree for you. ASB, ASB, ASB. So what we have got, sorry, we should not go till this. See, we have got double A double B and we want triple A double B now. So this S should go to A. So what we have got, triple A double B. Okay, this is the yield of the parse tree. So what is the height? Height, I think you already know. Height is the path length of the longest path. Okay, what is the height? Let me define it. Length of longest path, length of longest path from root to leaf. Okay, length of the longest path from root to leaf. So see the length of longest path, 1, 2 and 3. So here height will be 3. That's it. Okay, so height of the parse tree will be 3 here. So similarly the question can be A power 5, B power 2, so length will be 5 and so on. You can check it out. Okay, so 3 is what? This power 3 is becoming height. See, this is a question, and by coincidence I'm going to I'm linking that A power 3, so height is 3. So similarly you can check A power 5, height will be 5 and so on. Okay, so okay, that's it. This is the height. So height is what? Length of the longest path from root to leaf. Next question. S implies double S or A while deriving string triple A, how many parse trees are possible? See, make some stars on this type of question. These are very, very important for gate point of view as well as UGC-Net point of view. Many competitive exam ask such kind of questions. So while deriving triple A, how many parse trees are possible? See, this is a very simple question. If you want to derive triple A, you have to write this production rule, S implies SS. Then again, you have to do S implies SS. Now you have to replace each S by A. Okay, so this is one of the way. Another way can be, or let me write it properly. Second, so this is the first way, and the second way can be S implies SS. Now try to replace this S by double S. Now this is obvious thing. So A and A. So I hope I have made the point clear. So total we have 2 parse trees. So answer for this question will be 2 parse trees. Okay, why 2 parse trees? Because see here, very simple scenario. S implies SS. Now first way is replace this by this S by SS, and second way is replace this S by SS. Okay, so hence we have 2 ways. So this is a very simple question. Let's jump to next question. S implies AS, SA or A while deriving string triple A, how many parse trees are possible? So again, very simple. S implies AS or SA, na? So first time you apply AS, then again you apply AS, then again you apply A. So you got a triple A. This is the first way. Now second way can be what? I think you have guessed it. S implies AS, then replace this S by SA. Okay, and replace this S by A. This is the second way. What about my third way? Third way is, see, first time we have replaced, see, we want triple A now. So I have written this production 2 times and the last S was replaced by A. This was the first way. S implies AS, S implies AS, then S goes to A. Second way can be S implies AS. Okay, S implies AS. And now you apply SA. In place of AS, you apply SA. You got the second parse tree. And obviously this S will be replaced by A. So you get the second parse tree. Third parse tree can be S implies SA, S implies SA, and replace this S by A. And the fourth, I think you have already got it right. That is S implies SA, then AS, and then A. So we have total 4 parse trees. So answer for this question is 4 parse trees. And how I have got it, I think you have already got the idea. Okay, so apply this 2 times. This is the first way. Apply this 2 times. This is your fourth way. Sorry, second way. Sorry, third way. Third way. S implies S 2 times. Nah? So this is your third way. Okay, so one time this, one time this, then one time this, one time this. So I hope I have made the point clear. So you have got it right. Okay, so we have 4 parse trees. Or if you are not able to get it, please rewind the video and watch it again. You will get the answer. Next, LMDs and RMDs. See, to explain this concept of LMD and RMD, I have taken this example. LMD means what? Leftmost derivation. RMD means rightmost derivation. So let me write it properly. LMD means leftmost derivation. LMD means leftmost derivation. Similarly, RMD means rightmost derivation. Okay. So now let me give you some example. This is a grammar, and I want to generate a string A plus B star C. What are the ways? So let me give you some idea. You apply S implies S plus S. Okay, now you have two options. Either you expand this as first or this as first. So leftmost means what? Each and every time, whenever you have a choice, you have to expand leftmost symbol first. So I will expand this non-terminal S first, and then I will expand this. Okay, I will first expand this and this, then this. Why? Because leftmost, as the name suggests, you have to expand leftmost non-terminal first. So you have to expand this first. So let me expand it. So now this will become what? A plus B star C. Now we want A plus B star C. So S implies A plus S. Now you have only one choice. So see, if we have two choices, then you have to take the leftmost. If you have only one choice, that means only one non-terminal. Then obviously this is the leftmost. Now, so we have to apply, or you have to expand this only. So when we will expand this, we will get what? S implies A plus S star S, because we need B star C. So now again, see, we have a choice. So leftmost derivation means what? Leftmost symbol you have to expand every time. So I will expand this first. So what will be the answer? A plus B star S. And now we have only one choice left. So we have to expand it A plus B star C. So this is what I have done. I have done leftmost derivation. So whenever I have a choice, or you can say we have two or more non-terminals, then we will expand leftmost non-terminal first. That is known as, you can say, leftmost derivation. What about my rightmost derivation? Similar idea of rightmost, similar idea. See, I will apply this S plus S, rightmost, na. So you have to, we have a choice. So I will expand rightmost first. So S will be expanded. S implies what? S star S. So S plus S star S we have got. Now rightmost means what? Again, see, rightmost is this now, or you can say last symbol. So you have to expand this first. So what will you get? S plus S star C. Now again you have to expand. See, again we have a choice. So I will expand the last symbol, or you can say last non-terminal or rightmost non-terminal. So S plus B star C. Or now we will expand this A plus B star C. Okay, I hope I have made the point clear to all of you. So this is what? This is leftmost derivation, and this is what? Rightmost derivation. Okay, so is there any other way to find leftmost derivation? Yes, obviously I have another way also. So let me do it for you properly. Okay, so let me do it properly. I will write, or let me use a different color also, another LMD, or let me label them properly also. This is LMD1, RMD1. Now I am showing you LMD2. Now I am showing you LMD2, leftmost derivation 2. S implies S star S. Leftmost, we have to expand leftmost now. So you will expand it like this. S implies S plus S star S. S plus S star S. Now I will expand this S, because we have to expand leftmost now, or you can say first non-terminal. So this S will be replaced by A plus S star S. We will expand this now. A plus B star S. We will expand this now. A plus B star C. We have got the string. Okay. So each and every time I have expanded the leftmost symbol only, or leftmost non-terminal only. Okay. What about my RMD2? RMD2 will be what? S implies S star S. RMD, na? So you have to expand this first. So you will get C. So S star C. Now you will expand this. S plus S star C. Rightmost, na? So you will expand this. S plus B star C. You will expand this now. A plus B star C. So we have got the string A plus B star C. Okay. So this is RMD2. So for this string, A plus B star C, see here carefully, A plus B star C, we have two LMDs and two RMDs. Okay, so for this string, we have two LMDs and two RMDs. Please note it down carefully, or let me do everything, put everything on one slide so that you can note it down properly. Please note it down properly. Okay, so I hope I have made the point clear. What exactly is LMD and what exactly is RMD? So LMD and RMDs are nothing but ways to derive string from a grammar. Okay, so this was a string A plus B star C. So I have these are ways to deriving string. Okay, so let me give you one more idea so that you get everything properly. So tell me this thing. What about this scenario? S implies S plus S. Now I expand it as A plus S. Now I expand it as A plus S star S. Now I expand this A plus S star C. Now I expand it A plus B star C. So this is neither LMD nor RMD. Why? Because first time, let me use a different color. First time I have a choice. So I have expanded this. So each and every time I have to expand left now. Now see, this was the only one non-terminal. So there was no choice at all. I have to expand it by S star S. Now, since we have a choice here, we should expand this, but I have expanded this. So this is neither leftmost derivation nor rightmost derivation, because if it was leftmost derivation, then I have to expand this as first, but I have expanded this as first. Hence, this is not LMD. And obviously, this is not RMD, because if it was RMD, then we should have expanded this first. But I have expanded this. I hope I have made the point clear. Please note it down carefully. I'm jumping to next slide. Okay, so now we have built the background for ambiguity. We have studied two terms, parse tree or derivation tree. Second is LMD and RMD. Now see the definition of ambiguity. See, ambiguity says a CFG will be ambiguous. See here carefully. A CFG will be ambiguous if for any string W belong to LG, you have to find at least one string. If that is the basic meaning for any string, you have to find at least one string W belong to LG. And for that, we should have at two or more parse trees, or two or more LMDs, or two or more RMDs. Okay, so let me give you some intuitive idea here. See, we have a grammar, and this grammar is generating this language. Language is what? Set of strings. So these are strings which are generated by this grammar. You have to find at least one string in this language. We have to see, this is a, let us suppose this is a string. So we have to find at least one string in this language for which we should be able to get two or more parse trees, so greater than or equal to two parse trees, or greater than or equal to two LMDs, or greater than or equal to two RMDs. So anything can be done. So for this string, either you have to make two or more parse trees, or you have to make two or more LMDs, or you have to make two or more RMDs. Then we will say that this grammar is ambiguous. So when can I say grammar is ambiguous? You have to find a string. Okay. And for that string, we should be able to design two or more parse trees, two or more LMDs, or two or more RMDs. Okay. So I hope I have made the point clear. So let me read this definition again for you. A context-free grammar will be ambiguous if for any string W belong to LG, we have two or more parse trees, two or more LMDs, or two or more RMDs. Okay. Okay. Now next definition will be, when can I say grammar is unambiguous? So of course I have to complement the statement. No? When can I say this grammar is unambiguous? Then if for each and every string in the language, we should be able to get exactly one parse tree, or exactly one LMD, exactly one RMD. Okay, for each and every string in the language. So see, I have written this point clearly. A context-free grammar will be unambiguous if and only for all W belongs to LG. For all W belongs to LG. That means each and every string in the language, we have exactly one parse tree, or exactly one LMD, or exactly one RMD. Okay, I hope I have made the point clear. Okay, now for a string W belong to LG, this is very, very important point. That's why I have written, na, see, why you should ask me question that why I have written or here. One or more parse tree, or exactly one LMD, or exactly one RMD. So see, I have given the reason for it. For a string W belong to LG, if we have any string W belong to LG, number of parse tree will be equal to number of LMD, that will be equal to number of RMD. This is very, very important point. Please note it down carefully. Let me put this in a box and make some stars for you so that you get the proper idea. Okay, number of parse trees, that should be equal to number of LMDs, that should be equal to number of RMDs. So each and all these three are equal. So directly and indirectly, what I want to say, if for this string I am able to get two parse trees, then definitely I should get two LMDs, and then definitely I should get two RMDs. Okay, so let me give you some example. If for this string W, I am able to design two parse tree. What does this mean? If I am able to design two parse trees, that means what? I will definitely get two LMDs, and I will definitely get two RMDs. And another way can be, if for string this W, if for this string W, I have got two LMDs. If I have got two LMDs, then that means what? I will definitely get two RMDs, and I will definitely get two parse trees. Similarly, for this W, if I am able to get two RMDs, if I am able to get two RMDs, then definitely I will get two LMDs, and then definitely I will get two parse trees, and so on. Okay, so I hope I have made the point clear. So for any string W, if you are able to, so how to identify that given grammar is ambiguous or not? You have to find a string W, and for that W, if you are able to design two parse tree, that's it. You will say that grammar is ambiguous. Or if you are able to design two LMDs for that string, you will say grammar is ambiguous. Or if you are able to design two RMD for that string, you will say grammar is ambiguous. That's it. Because two parse tree directly and indirectly means two LMDs also and two RMDs also. Two LMDs means two RMD also, two parse tree also. Two RMD means two LMD also, two parse tree also, and so on. So I hope I have made the point clear to all of you. If you are still not able to follow, please rewind the video and watch it again. Okay. So now next point. Next point is what? So obviously now what exactly is LMDs and what exactly is RMDs? So I can obviously say that LMDs and RMDs are nothing but, see here, LMDs and RMDs are nothing but one of the way of checking grammar is ambiguous or not. Because I have already told you, when can I say grammar is ambiguous? If for a string W, we are able to design two LMDs or two RMDs or two parse trees. Well, two or more parse trees. No? Okay, so grammar is said to be, let me do it again, or let me say it again. A grammar is said to be ambiguous if we are able to design for any string W in LG, we should be able to design two or more parse trees, two or more LMDs, two or more RMDs. That's it. Okay, so LMDs and RMDs are nothing but one of the way of checking grammar is ambiguous or not. Okay, I hope I have made the point clear to all of you. Let me put everything on one slide so that you can note it down. Please note it down carefully. Okay, now let's jump to the question. See, if for any string W belong to LG, we are able to find one LMD and one RMD, then grammar is ambiguous. Is this statement true or false? Please pause the video and try to answer it. I know most of the students will say true, but actually this statement is false. Why this statement is false? See, for every string, if that string belongs to language, then that string will obviously have one LMD and one RMD, or you can say at least one LMD and at least one RMD. See, this is a statement I have written on the next slide. See this statement. If W belong to LG, then there exists parse tree and LMD and RMD. That means what? Minimum one LMD, minimum one RMD, minimum one parse tree we should always get if that W belong to LG. And obviously, if W does not belong to LG, then obviously we won't be able to get parse tree or LMD or RMD. Okay, but if W belong to LG, then we should definitely get at least one. This is, you know, I think you should know this symbol according from your logic from discrete mathematics. This is what there exists now. So at least one. So I should say at least one. If W belong to LG, then at least one parse tree we should get, and at least one LMD and at least one RMD we should definitely get. Okay, so if we get one LMD, one RMD, and one parse tree, then obviously that for that string, so then obviously we cannot decide anything. No? But if for each and every string in LG, we are able to get exactly one parse tree and exactly one RMD and exactly one RMD, then we will say that grammar is unambiguous. Okay, I hope I have made the point clear. So let me give one you can say example also, so that you get the proper idea. S implies ASB or null. Take a string, say double A double B. For this string, what about my LMD? S implies ASB. Do we have any choice here? No, only one non-terminal. So we have to expand it. That's it. So this will be AASBB. Now, do we have any choice? No, we do not have any choice. So we have to expand this as only. So that will be, it will go to null. So we will get double A double B. All right, let me write it properly. Double A double B. Okay. So now for string double A double B, I will say this is LMD. Is it correct statement or not? Obviously, this is LMD because we have no choice. So I will say I have expanded leftmost non-terminal. If we have only one non-terminal, I will say it is leftmost. Okay. Now, can I say that this is RMD also? Obviously, this is RMD also. Why? Because we have only one non-terminal. We have only one non-terminal. So I will say that this is the rightmost. If we have only one student in the class, then I will say that obviously this student is first also and this student is last also. Okay, so this is the same logic here. This is LMD also and this is RMD also. Okay, so if you want to design a parse tree, then obviously I will say like this: S implies ASB, S implies ASB, and S goes to null. Okay, so see here for this string, there is no other choice now. So for this string double A double B, we have exactly one LMD. This is exactly one RMD also. Same, this is LMD and this is RMD, and this is what parse tree. Okay, so now can I decide that this because for this string we are not able to get two or more LMD, two or more RMD, or two or more parse tree, so this grammar is unambiguous. No, this is not the case. For each and every string, we should be able to get exactly one LMD, exactly one RMD, and exactly one parse tree for each and every string. And see, by intuition, you will be able to guess. We have no choice here, na? We have to expand this as only. So for AB, see, for the smallest possible string in LG, LG will be what? First of all, tell me what LG is what. So please see my previous lectures, construction of grammar. You will get the idea. LG is A power n, B power n, such that n is greater than equal to 0. This is LG. Okay, now see, this is because this is LG. So smallest possible string is what? Null. So S implies null, only one parse tree. There is no way out. So next string will be AB. So A, S, B, and S goes to null. You will get AB, and there is no way out. No other way to generate AB. Third is double A double B. Again, we have designed only one parse tree, only one LMD, and only one RMD. Triple A, triple B, and so on. You can check it out for some strings, and you will get the intuitive idea that for each and every string, we will get exactly one LMD, exactly one RMD, and exactly one parse tree. Hence, this grammar is unambiguous. Okay, so I have proven it that this grammar is unambiguous. Okay, I hope I have made the point clear to all of you. So for each and every string here, we are getting exactly one LMD, exactly one RMD, and exactly one parse tree. Okay, so this statement is false. I hope I have made the point clear to all of you, because for any string W, we use the word here for any string W. So I have got a string W. For that string, we have got exactly one LMD, exactly one RMD, and exactly one parse tree. So can I say this grammar is unambiguous? No. Okay, we have to take other strings also, and for each and every string we have to prove exactly one LMD, exactly one RMD, exactly one parse tree. Okay, now see the question. If for any string W belong to LG, we are able to find one LMD, one RMD, then grammar is ambiguous. No, this statement is obviously false. We cannot say that grammar is ambiguous. Okay, so the question should be the grammar is unambiguous. No, again I cannot say grammar is unambiguous if for any string W. Okay, so I should say for all string W belong to LG, we are able to find one LMD, one RMD, then grammar is unambiguous. Okay, so I hope I have made the point clear to all of you. So let me write it properly if you are not able to get it. or let me say it slowly so that you can write. I should say, if for every string w belong to LG, if for every string w belong to LG, we are able to find one LMD and one RMD only. We are able to find one LMD and one RMD only, then grammar is unambiguous. Yes, that statement will be true. Okay, please note it down carefully. Okay, so one LMD, one RMD. If W belong to LG, then we should be able to get at least one LMD and at least one RMD. I have already told you, if W belong to LG, if the string is in LG, then LG means what? Language generated by grammar G. Okay, so this is your LG, na? If this is a grammar, then this is your LG, A parent, B parent. Okay, so if W belong to LG, then there exists at least one parse tree and at least one LMD and at least one RMD. So if we are getting for every string exactly one parse tree, exactly one LMD and exactly one RMD, then we will say grammar is unambiguous. Okay, I hope I have made the point clear to all of you. Please note it down carefully. Please do not get confused. If you are still not able to follow, please rewind the video and watch it again. I'm not going to explain it again and again. Okay. Okay, so there should be at least one parse tree. Okay, and there should be at least one LMD and at least one RMD. Then we will say that W belongs to LG. Okay, but if exactly one parse tree, exactly one LMD, exactly one RMD for each and every string in the language, then we will say that the grammar is unambiguous. Okay. Okay. Let's move to next slide. But I have repeated many times. If again you have problem, then please rewind the video and watch it again. Okay. Now next question. S implies S plus S star S or A. Is this grammar ambiguous? This is very simple. See the previous slide. I have already told you about it. For this grammar, okay, see here, for this grammar, we have two LMDs, two RMDs. So that means what? For this string, we have got two LMD, two RMD. So obviously this grammar is ambiguous. Okay. So see here, we have got two LMDs, two RMDs. Then by guarantee, with guarantee, I can say we will get two parse tree also. If you want, then I can make that these parse tree also for you. So from LMD, I can design parse tree. And for RMD also, I can design parse tree. So this is your choice that you want to follow this LMDs or RMDs. So let me do it for LMDs, and for RMDs, that will be homework for you. So S implies S plus S. S implies S plus S. You have expanded this S first, na? See here, leftmost first, na? So no problem. You will say S implies A, and now we will expand this S as S star S. Now this S will be replaced by B, and this will be replaced by C. So this is your first parse tree. What about my second parse tree? S implies, see here, S star S. See here properly. From LMDs, I'm designing. From RMDs, you can do it your own. S implies S star S. Then this S will be replaced by S plus S. Now this S will be replaced by A. Then this S will be replaced by B. Then this S will be replaced by C. So A plus B star C. Okay. So with guarantee, I have said you, and I have proved this also, that for this string A plus B star C, we have got two LMDs. Then obviously we should get two parse tree, and we have two RMDs also. So we should get two parse trees only. Okay. So everything will be two. See this slide. Number of parse trees is equal to number of LMDs is equal to number of RMDs. So everything will be 2, na? So we have two LMDs, so obviously two parse tree. We have two RMDs, obviously two parse tree. So these two parse tree will be for these two RMDs also. So you can check it out yourself. S implies S plus S. You have to expand this S first. So you have expanded like this, S star S. Now this S will be replaced by C. This will be, this will be. So same parse tree for this RMD. Okay. The only thing is, when for LMD I was making this parse tree, then I said S plus S. Then this S was replaced by A first. But if we are doing it for RMD, we will say S plus S, then we will expand this S first, S star S. Okay, but anyhow, the picture of the parse tree will be exactly like this only. Okay, I hope I have made the point clear. And for this RMD, S implies S star S, then S goes to C and so on. So see, same parse tree for this RMD. Okay, so how I will say for this RMD, how I will say this is parse tree. This is the first production rule. S implies S star S. Now you have to replace this S by C. Now, so this is the second production rule applied. then S plus S, this will be the third production rule applied, S plus S. Then this S with B, so this is your fourth production rule, and this is your fifth production rule. Now I have labeled it, so you will get more idea. So please note it down carefully. Okay. So now let's jump to our question. S implies S plus S, S star S or A. Is this ambiguous? Obviously, this is ambiguous. We were having B and C also, so we have only A here. No problem. Okay. In the previous question, we were having like this, na, A or B or C, and the string was A plus B star C. So here I have only A. No problem. Okay, no problem. So what I will do? See, I will let me erase it first. Okay. So that we get question neat and clean. Okay, so so I will take the string as A plus A star A. Okay, so the easiest way is, forget about LMD RMD, easiest way is parse tree. So try to make two parse tree for this string. S implies S plus S, then A, S star S, A. So see here what we are getting. A plus A star A. This was the string. Now we have got this parse tree. What about my second parse tree? S implies S star S. S implies S plus S. S plus S. No? Then A, then A, and then A. See here properly what we have got. A plus A star A only. Okay, so this is the second parse tree. We have got two parse trees now for this string. That's enough. I will say that the grammar is ambiguous. Okay, so this was very simple point. And how I got the idea about this string only? This is all about intuition. Okay? The more you practice, the more you will get the things. This is all about intuition. So you have to practice more and more. Okay, now let's jump to the next slide. So see here, this is very, very important point, and this point came many times in GATE as well as NET and other competitive exam. So please make some star on it. Checking CFG is ambiguous. This is known as ambiguity problem of CFG. Ambiguity problem of CFG means what? Checking the given CFG is ambiguous. Okay, is an undecidable problem. This is an undecidable problem. Undecidable problem means, please note it down carefully. When can I say a problem is undecidable? No one in this world will ever be able to write algorithm to solve the problem. Algorithm to solve the given problem. So when can I say a given problem is undecidable? I will say that the given problem is undecidable when I will say that no one in this world will ever be able to write algorithm to solve the given problem. This is a very big statement. I'm not saying that I am not able to decide or you are not able to design algorithm. I'm not saying it that I am not able to design algorithm, you are not able to design algorithm and so on. I'm saying this is a very strong statement. See here carefully. No one in this world will ever be able to write algorithm to solve the given problem. No one will be able to write. Will ever. That means not today, not tomorrow, not 10 years, not 20 years down the line. Will ever. No one will be able to write algorithm for it. Okay. So obviously, if I'm saying this statement, then this statement should be formally proved, and it is formally proved also. We will, of course, we will not go into the formal proof of this statement. That why this context-free grammar, ambiguity problem of context-free grammar is undecidable. We are not going into formal details. This is out of scope of this course. Okay, and but in chapter 3 or sorry, chapter 4, Turing machines and decidability, I will give you a hint about it. Why this is undecidable and so on. Okay, or why no one in this world will be able to write algorithm for it. Okay, we will prove it, but not formally, but intuitively. Okay. Okay. Now, so since this is undecidable problem, and I have told you that no one will be able to write algorithm for it, so obviously the only way is you have to apply intuition. Whenever a question came that is this grammar ambiguous or not, so I do not have any algorithm. That means I don't have any fixed procedure or fixed steps that you follow these steps and you will get the answer. I do not have any kind of thing like this. So you have to do it, or by intuition only. Okay, so no one can teach you some small tricks and small things that you apply this and so on and you will get the answer. But okay, this won't work. Of course, small tricks or few tips and tricks I will give you, but not exact procedure or exact algorithm, because we do not have algorithm for it. This is undecidable problem. Okay, so let me jump to next slide. As simple as SS or A. Is this grammar ambiguous? Yes, obviously this is ambiguous. Take a string. See, if you have practice, you will immediately get the answer. See, let me do it step by step for you. The smallest possible string generated by this grammar is A, and for that string we have only one way, that is as simple as A, only one parse tree. Next string is double A. Double A, we have only one parse, that is as simple as SS, as simple as A, as simple as A. So till now we do not got any success. That means we have only one parse tree. So if obviously if only one parse tree, then obviously one LMD and obviously one RMD. Okay, so in case if I do it in terms of LMD and RMD, then I can say like this: S implies SS, because LMD na, so leftmost symbol first, AS, then AA. You will get like this. This is your LMD. What about my RMD? S implies SS, RMD. The rightmost will be expanded first, SA, then we will get this. Obviously, both are same, na? So no problem. Actually, these are not same, but I am saying it as this is your exactly one RMD, and you have got exactly one RMD. Sorry, LMD. This is your LMD, na? Let me write it properly for you. Okay. Yeah, this is your RMD. This is your LMD, and this is your parse tree. And I have told you many times repeatedly that if only one parse tree, then obviously one LMD and obviously one RMD. Okay, so that's it. So let me take another string, that is AAA. Next string will be AAA from this grammar. You can check it out. So AAA, obviously we will get two parse tree, na? As simple as SS. I have already given this similar question. Na? See here, see the previous slide. As simple as SSA, as simple as SS or A. So while deriving AAA, how many parse tree? So I have given you idea about two parse trees. Na? Okay, so obviously we have got two parse trees, so grammar will be ambiguous. Okay, so let me do it now properly. For AAA, S implies SS, or you can expand this as like this, or you can expand this as like this. So obviously you will get two parse trees. Okay, since you are getting two parse trees, so you will get exactly two LMDs and exactly two RMDs also. This is your parse tree now. So if you want LMD, I will say like this: LMD number one will be what? S implies SS, SS, then A, and then A. Like this. This is your LMD. Now leftmost I have expanded. Another LMD will be what? LMD number two. S implies SS. Okay. So this S will be replaced by A. Okay. I have replaced this S by SS now. Like this now. Now I am replacing it by A. We have to expand leftmost now. No problem. I have expanded this by A. Now this S will be replaced by SS. Now we have a choice here. So I will expand this as first. Okay, see here. See, as simple as SS, we have a choice. So we have to expand leftmost. So I have expanded leftmost as A. Now we have got this S. Now, so okay. So let me do it step by step. Otherwise, you will get confused. Okay, let me do it step by step. I have expanded it. S implies A, and this S will be this same S only, because in each step I am doing one thing. Na? We have to apply one production in one step. So S implies AS. Now this S will be expanded as SS. Now we have a choice. Now this S will be expanded as A. Now this S will be expanded as A. So we have got two LMDs for the same string AAA. Hence, the grammar is ambiguous. Okay, or that's enough na, to prove grammar is ambiguous. This is enough. You have made two parse tree for AAA. This is enough. But I am just showing you, or I am just proving you that you have got two parse tree number one, parse tree number two. So for each parse tree, we will have a LMD. So for according to this parse tree, we have this LMD. According to this parse tree, we have this RMD. Sorry, for the according to this parse tree, we have this LMD also. So every parse tree is related to LMDs. Similarly, RMDs is homework for you. I am not doing it because it is just wastage of time. This is obvious also. For this parse tree, try to generate RMD. For this parse tree also try to generate RMD. Okay, or it will take just a minute only. So let me do it properly for you. So RMD number one. RMD number one. According to this parse tree, I will say S implies SS, S goes to A. Okay, now I will expand this SS, SSA. Now I will expand this SS, SAA. Now this SS AAA. Similarly, what about my this RMD number two? I will say S implies SS. This S will be replaced now. So I will replace this S by double S. See here carefully. This S is this S is replaced by this S is replaced by double S. So I will expand this S by double S. That's it. So it's just a representation and nothing more than that. Okay. So now this S will be replaced by A. This S will be replaced by A. This S will be replaced by A. So we'll get AAA. Okay. So I hope I have made the point clear. So let me put everything on one slide so that you can note it down carefully. Okay. Please carefully note it down. I hope everything is visible to all of you. Please note it down carefully. Next question. S implies AS, B or null. Is this grammar ambiguous? I have already told you this grammar is unambiguous. See the previous slides or rewind the video and watch it again. I'm not going to repeat it again and again. This grammar is unambiguous because we will obviously get only one parse tree. What about my LG here? If you are not following it, let me do it in a faster manner. LG will be what? A power n, B power n, such that n is greater than equal to 0. How I am getting this LG? Please watch my previous lecture. Construction of grammars, you will get the idea. Okay. So this is your LG. So smallest possible string is null. Only one parse tree for null. Next will be AB. So only one parse tree for AB. Okay. So next string will be AA double B. Only one parse tree for AA double B also. Because we do not have any choice here. Please see it carefully. In right hand side, we have only one non-terminal, that is S. So I have to expand this S only. I have no other choice. So this grammar is unambiguous. Okay. So this was the intuitive idea that why this is unambiguous. Now let's move to next question. See here, S implies this. Is this grammar ambiguous? If you have a good practice, then you will obviously get the answer immediately. How you will get the answer immediately? See, let me say it this way. S implies AS, BS, null, and this is A. So this A can go to null also. That's it. I have got the idea that for null string, we will have two parse tree. That is what S implies null. This is the first parse tree. And for second parse tree will be S implies A implies null. So we have got two parse trees for null. Hence this grammar is unambiguous. Sorry, this grammar is ambiguous. Okay, so this grammar is ambiguous. So let me tick it. This grammar is ambiguous. How I have got this idea in a very faster manner? See here carefully. RHSC, we have a null. So can I get null here? Yes, A can be replaced by null. So by two production rule, we can generate null. That's it. So two production rule on RHS. See, RHS of two production rule are exactly matching. That means what grammar will be ambiguous. This is a small shortcut, or you can say small trick. I have already told that I will give you some small tips and tricks. So this is a trick that see AS and BS. So obviously these two production rule will generate different kind of string. But what about this? This will generate null. What about this? A can be replaced by null also. So you will get null two times. So obviously we will have two ways to generate null. So the grammar is ambiguous. This is a shortcut. Please note it down carefully. Next, S implies A or A implies A or null. What about this? Is this ambiguous or not? Okay. So obviously you will get the idea. See here, S implies A. This right hand side is A. Now this is AA and this A can go to null. So we will get A two times. So small a, to generate small a, we have two ways. So obviously grammar is ambiguous. Yes, this is the correct answer. Okay, so if you are not able to get it, please let me do it properly for you. A goes to null and this is what S goes to A. That's it. So we have generated two parse trees for A. So grammar is ambiguous. Okay, so the trick was, see here carefully, AA and small a. So small a we have, okay, no problem. What about this? So this capital A can be replaced by null. So we will get small a again. That means what? RHS of production rule is matching. So obviously you will get two parse trees. We have got the two parse trees. So grammar is ambiguous. Let's move to next question. S implies ASB, BSA, SS or null. Again, very, very important question and very, very beautiful question. Please make star on it. And the same question was asked in UGC-Net also and GATE also. So is this grammar ambiguous? Yes, obviously this is ambiguous. How will you prove it? See, this is very, very simple. Whenever you see S implies SS and null, I will say 1, 2, 3. Forget about 2, 3, 1, 2, 3, 4 parse trees. I will say infinite parse trees. Infinite parse tree for null. How? See here carefully. S implies null. This is the first. Second parse tree can be S implies SS, and this S goes to null. This S goes to null. Null dot null is null only. So that's why we have got two parse trees. Now see here. S implies SS. See, expanded this as SS, null, null, and null. Null dot null is null only. Fourth parse tree, S implies SS, S implies SS, null, null, null. Fourth, then fifth, then sixth, and so on. You will get infinite. I hope I have made the point clear. Okay, so you have done like this now. This S was expanded as SS. See here carefully. This S was expanded as SS. Now next time this S was expanded as SS. Now next, if you want to generate fifth parse tree, then both will be expanded as SS. Then you will get 4 times null, and 4 times null is nothing but null only. Okay, so let me give you one more idea. S implies SS, S implies SS, S implies SS, null, 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 null. You will get your fifth parse tree, and so on. I hope now I have made the intuition, and I have given you proper idea. So now you can easily design your parse trees. So infinite parse tree. Now see this carefully. Infinite parse tree for null. Now, obviously, I will say for each and every string, we will have infinite parse tree because we have got infinite parse tree for null. This implies infinite parse tree for every string. For every string. Why? Because I can put null anywhere in the string. See here carefully. For AB, let me give you idea, then you will get the answer. AB, for string AB, you will say S implies ASB, and this S goes to null. You have got one parse tree. What about my second parse tree? Very, very simple. S goes to ASB. For null, I have already told you infinite parse tree. So obviously you will get infinite parse tree. I will say that S implies SS. This S goes to null. This S goes to null. So you have got AB and so on. Please expand it yourself. You will get the idea. Okay. So this is very, very important point. Please note it down carefully. So this grammar is obviously ambiguous. Okay. Next. ASB, BS, AS, BS, BS, AS, and null. Is this grammar ambiguous? Yes, this is also ambiguous. Again, very, very simple. See here. Whenever we are using this production rule, you will get AB. And whenever we are using this production rule, you will get BA. Okay, so can you tell me the language generated by this grammar? LG will be what? LG will consist of all those W's such that number of A in W is equal to number of B in W. This is very, very important grammar. Please note it down carefully. So how I can say like this? Because see here, AS, BS, BS, AS. If we apply this production rule, you will get A and B. That means equal A is equal B. Again, whenever you apply this production rule, you will get equal BA. So again, equal A is equal B. Okay, so all those strings will be generated. Now, in AB, you can inject here AB, BA, and here you can also inject here also AB, BA, and so on. I hope I have made the point clear. Please try to take strings, and this is homework for you, and you have to prove yourself that why this grammar is generating all those strings over A and B in which number of A's and B's are equal. Okay, this is homework for you. Please try to get it properly. Okay, now I want to prove that this grammar is ambiguous or not. Obviously, this grammar is ambiguous. Okay, so let me take some string. What exactly we are doing? S implies, see here, AS, BS. Okay, AS, BS. If you have applied this, now you can inject here anything. This S can be replaced by AB or BA and so on. Nah? So let me take a string like this, AB, AB. Okay, this is very simple string. Now, this AB, AB can be realized like this, AB followed by AB. That means what? You have got AB now. Followed by AB means what? AS, BS. Okay, so now this S will be replaced by null, this S will be null, this S by null. So you will get AB, AB. This is your first parse tree. Second way is what? AB, AB. Na? Again, let me write it AB, AB. So BA. So within AB, we have a BA. So obviously now you have got the idea that ASBS. You will write ASBS. Now this S, because we need in between BA, na? So this S will be replaced by BSAS. Okay, so please expand it properly. You will get ABAB. So we have made two past trees for ABAB. This grammar is ambiguous. Okay. Okay. So we just need only one string. Now you just try to find one string, and that is obviously by intuition. How I have got it. How I have got it. Please, this is nothing but intuition only. You have to think about it. You will get the answer. Okay. Now let's move to next question. A, B, 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 null, and so on. So this is a grammar. So I will apply shortcut here. The same shortcut which I have already told you. See, see this B, right hand side is B, and this is what BS, and S can be replaced by null. So for generating B, we have two ways. From A, generating B, we have two ways. That's it. I have got the answer. So now string, we will try to jump to this capital A. For jumping this capital A from starting from a C, every string, if we want to generate any string, we have to start from start symbol now. So from start symbol, we want to jump to A at a very faster pace. So we will apply this production rule. S implies AA. S implies AA. From A to generate B, we have two ways. That is like this, and another can be like this. So for generating AB, we have two pass tree, and the grammar is ambiguous. Hence the grammar is ambiguous. I hope I have made the point clear to all of you. Similarly, here also you have the same thing. A and AS. S can go to null. So two ways. Okay, so to generate A from B, we have two ways. So you can think like this also. S implies BB. This B can be replaced by A. This is one way. Another way can be BB, and this B will be replaced by AS. This S will be replaced by null. So for BA string also, this is for BA string, we have two pass trees. For AB string, we have two pass trees. I hope I have made the point clear. This was just for the practice I have given you, that for BA also, but we do not need to go, we need not find another string example which have two or more pass trees and so on. You just need to find only one string, and I have got the string AB, which have two pass trees. That's it. So I will get a conclusion that this grammar is ambiguous. Okay. Just for the proper understanding, I have given you another example that string can be BA also. This is not B9. This is BA. Okay. Yeah, this is BA. Let me write it properly for you. Otherwise, you will get confusion. This is BA. Okay. Yeah. So this is AB and this is BA. For AB also, we have two pass trees. For BA also, we have two pass trees. Okay. And we just need to concentrate only on one string. And for AB, we have got two pass trees. You can stop and you will say that grammar is ambiguous. You have got the conclusion. But just for the sake of proper understanding, I have given another example, that is BA. Okay. Okay. So let's move to next question. S implies S within bracket SS or null. See again here, SS or null. I will say infinite pass tree. I have already told you in this slide. Please see this slide. See here. Please copy paste everything here. I'm not going to explain it again and again. Okay. So this is what? This is a very beautiful example. This is a language. See, I have already told you ambiguity of grammars. See the topic. See the topic. Ambiguity of CFG, context-free grammars. Okay, so I have told you, when can I say a context-free grammar is ambiguous? I have told you about ambiguity of grammars. Now I will tell you one more important thing. See here, a CFL or context-free language. We are not concentrating on grammar, we are concentrating on language. A CFL is said to be ambiguous. That means a language is said to be ambiguous if we can't write unambiguous context-free grammar generating it. Okay, this is very, very important point. So a context-free language is said to be ambiguous if we can't write unambiguous context-free grammar generating it. Okay, please note it down carefully. So see, for a CFL, we can write, we have infinite ways to write grammar or to write context-free grammar. I have already told you many times. For any CFL, we have infinite ways to write CFG. And whichever way you try to choose, each and every way, or you can say each and every context-free grammar will be ambiguous. If this is the case, then I will say that this CFL is ambiguous. Okay, then I will say that this CFL is ambiguous. So now read it again. A CFL is said to be ambiguous if we can't write, we are not able to write unambiguous grammar generating it. That means what? Whenever we write a context-free grammar, that will be ambiguous only. Then I will say that the given CFL is ambiguous. So let me give you one example, and this is the best example. See the intuitive idea here. This is saying that A and B are equal, and this is saying that B and C are equal. So if S1 for starting from S1, you write a grammar which is generating this CFL, and with S2 you are writing a grammar which is generating this CFL. Now because of union, you have to implies S implies S1 or S2. S1 is generating what? This language. S2 is generating this language. S1 is generating this, S2 is generating this, and you have to apply S goes to S1 or S2 because of this union. Now this language is saying what? A and B are equal. This language is saying what? B and C are equal. Here this is saying A and B are equal. We are not concerned with C. C can be any numbers. So A and B should be equal. That's it. This is saying B and C should be equal. A can be any number. So what about the string like this? A, B, C, or double A, double B, double C, or you can say equal A is equal B is equal C, dot, 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 which have equal A is equal B is equal C is. So these strings can are present in this language also. This string is present in this language also. Why? Because we have A and B are equal. We are not concerned with C. A and B are equal. That means this string is present in this language. Similarly, this string is also present in this language because number of B's and number of C's are equal. We are not concerned with A here. Anyhow, number of B's and number of C's are equal. That means what? This string will be present in this language also. Now for this string, definitely there is a way to generate from S1. For this string, definitely there is a way to generate from S2. Hence, for this string, we will get definitely two parse trees. This is the intuitive way to prove that this language will be inherent, this language will be ambiguous. You should say ambiguous, or you can say inherently ambiguous also. Inherently ambiguous means what? You are not able to write unambiguous grammar generating. Okay, inherently ambiguous. You can use the word this also. Okay, let me write it. Inherently ambiguous. Inherently ambiguous. Okay, so I hope I have made the point clear to all of you. So this language is inherently ambiguous, and why this is inherently ambiguous I have told you. So if you are not able to follow, please rewind the video and watch it again. That's it. So this is all about ambiguity in CFG. In the next class we will study the next topic. Okay, that's it. Thank you so much. Bye bye.